Hello, everyone. Welcome to this maritime innovation update on our ship research simulator, where we will give you a short overview over the core concept overview and hydrodynamics. The presentation will be carried out by my colleague Ricardo. Just one hint before that, I ask everyone who is not part of this presentation to switch off their microphone and their camera. And just a hint that this presentation is recorded. So if you have a problem with that, just keep it in mind, please. Yes, just quickly to my person. My name is Paul. I'm the team Maritime Informatics at Fraunhofer CML. And my colleague who will do the presentation today is in the same team. He's working on hydrodynamics for our own research simulator, which we will present today. So I'll give the microphone to Ricardo, and the stage is yours.
Thank you very much, Paul, for your introduction. Well, as I say, my colleague Paul, I'm Ricardo Suarez. I'm member of Maritime Informatics. I'm responsible for ship hydrodynamic and ship simulator. And today I'm going to be the responsible to present this, the concept overview of the hydrodynamic of ship research simulator. I would like first start with a resume about the content of this presentation. That is, we're going to talk about the concept of the ship research. Also, we're going to take it out and evaluate the numerical model that is used for ship research simulator. The summary of the key points of the simulator, and concluding with some questions and conclusions. Well, let's start defining what is ship research simulator. Well, from the last year, Fraunhofer has decided to invest in generate on research simulator to carry out maritime and model simulations. And these simulators are going to be based on high accuracy hydrodynamic models to represent, as I say, with the best accuracy, the performance of the ships under different scenarios. SRS has the next functionalities. SRS allow us to modeling surface underwater vehicles. Also allow us to modeling offshore structures like offshore wind parks, etc., and port structures to be used later in the simulations. As I say, after to generate this model, we are able to simulate this to carry out offshore and port operations. Also allow us to improve and to work in vessel design, generating hydrodynamic models from the concept to a final product. And we are allowed to generate and evaluate different environmental conditions and different physical effects in the simulations. Ship research simulator has significant contributions, especially from the point of view that this tool was thinking to be used like a web service platform, connecting through the API, and allowed to carry out these simulations on it, and with the objective to improve and to have a tool with enough accuracy to design and develop vessels. Also, the contributions are significant in the field of the safety and efficient for marine operations. And also that is the future implementations to try to create a tool that allows to predict the full consumption of the real ships and how can be estimated by the simulator. Here, as I said, the concept of ship research simulator is based on web service, and under the idea that is based on microservice, and microservice are also having in consideration modularity and scalability. As we can see here, the ship research simulator allows us to carry out not only one ship, we can carry out as many instances as we want, well, in this case 100, without to have any low performance in the simulations in real time. And this is due to this modularity and scalability of the models. With this, we can simulate and plan in different maneuvers and investigate the hydrodynamic performance of the different ships. At the same time, ship result simulation allowed to collect data, not only from the numerical data, also allowed to collect data from different sensors of real ships and use this information to evaluate the levels of uncertainty between numerical models and real ships, as well as to a source of data for training machine learning algorithms. At this moment, we are doing implementations in the field of the coastal vision models, and also in the field of system identification to predict the hydrodynamic coefficients through the data from real ships and from computational fluid dynamics. One of the qualities of ship result simulator is that does not require a specific programming language. We can implement as much as we want according to the necessities. For the user, it is not necessary require knowledge of the other components of the ship result simulator. That is convenient because there are clients that are only attending for operations or for a specific kind of test, and they don't require to know about other modules of the system. As we say, communication via well-defined interface. We have microservers. This means that make that everything is modular. This means that we have a system that is listening what they are doing, the different components of the system, without necessity to be operating all the time and only be actuating when is required. Also, ship result access to full of capabilities. For example, simulator, data analytics, visualization. Also, in the future implementation of augmented reality, interaction, carry-out simulations, and so on. Now, that is my field of expertise, is the field of I'm responsible to generate the numerical models for the ship result simulator. And ship result simulator is a mathematical model that can deal with surface vehicles, underwater vehicles, and allowed to work in 3 degrees of freedom, 6 degrees of freedom, according if we want to carry out ship maneuverability or ship maneuverability in waves. Also, we have developed SRS from the point of view of the design operation. This means that if we are more focusing optimize one element of the ship, for example, like a rudder, or well, we can only focus more in some kind of specific maneuver, for example, in harbor, that maybe some pilot is new in this harbor and require a training, and this is something that we can carry out with SRS. The mathematical model, I would say the new thing is that SRS is not working only with one mathematical model, because follow the principle of modularity, we are allowed to have different mathematical models, and these mathematical models can be used like before. We are running, for example, 3, 4 different ships, and each one can operate with his own mathematical model. One thing is that all mathematical models are based in modular model or integrated model. This is how we approach the mathematical models. Modular model is a concept that we have modular for each hull, rudder and propulsion. They work independent internally, and we have the integral model that there are mathematical models based on Taylor series expansion. This means in this mathematical model we have a polynomial function that makes attractive for us, especially in relation to training machine learning algorithms, due to this integral model only require velocity terms to operate. This means that this is very attractive to use with real-time and machine learning algorithms. At the same time, ship research simulation can reproduce and simulate different environmental conditions like current, tidals, wind, and wave models. At the same time, we can simulate physical scenarios like deep and shallow waters, back effects, narrow channels, and ship-to-ship interactions. The simulation that is we can carry out with this mathematical model are presented now, but all of them, I have to say that all models are validated according to the regulations and especially in terms of ship maneuverability according to the IMO criteria. For example, here I would like to show you one when we analyze for the capabilities of the ship concerning to turning ability, yaw stability, course keeping and stopping capabilities. We make that all hydrodynamic model fulfill the requirements of IMO. Here I'm going to present a small. We are starting with a preparation of the hydrodynamic model, and when this is fulfilled the requirement from IMO, we pass to the final version in the ship result simulator to carry out the maneuvers and see that the ship is fulfilling the requirements. At the same time, this part is important for us because, as I said before, we can reproduce different scenarios like deep and shallow water condition. And here's an example about the hydrodynamic influence of deep and shallow water. As we can see here in the left side, we have a maneuver. That is for a rudder angle of 10 degrees and a starboard, and we can see the underwater clearance is for the shallow water condition is the 1.2, and for the deep water is the 4. Specifically, the underwater clearance is the difference between the water depth and the draft of the ship, and we can see the significance in the trajectory of the ship for the same rudder angle and for the same speed. Equal, we can see with the zigzag maneuver how maybe in this one is less obvious due to probably the rudder angle is higher than 10 degrees and the significance of the shallow waters we use with this amplitude of the rudder, but we can see that is significant the impact, and this has a strong impact when we want to do predictions about maneuvering in harbors or in confined waters. That safety is a main requirement. This means have a model that can predict with accuracy the maneuvers of the ships are very important. Here, for example, I would like to conclude this slide to show that the future work that we are working is in the area of the control for trajectory prediction and also for control the speed. With this tool, this is under development, but what we are going to do, for example, we can see that we have a predefined trajectory that could be the data from the AS, from the automatic identification system of the ship, and with this data we can use to evaluate the fuel oil consumption, and also according to the fuel oil consumption, which is the state of the ship concerning to CO2 emissions and so on. And this means this kind of tool allow us to optimize better the operations that we can evaluate before arrival to the harbor or any kind of their maneuver that we want to evaluate. Well, as I said, the key points here is the ship result simulator is an advanced tool for maritime model simulation, model and simulation of surface and underwater vehicles, offshore and port structures, saving time and resource design and development of the vessels, and to improve the safety and efficiency of the operations, and future implementation of fuel oil consumption and model emission reduction. Thank you very much. If you have some question, Paul, it will be a pleasure to answer them.
Yes, thank you, Ricardo, for your presentation. So now we have some time for questions. So if you want to know anything, you can just write in the chat. And the first question I will give directly to you, Ricardo, is if the SRS can account for drift due to currents? And if yes, just surface or maybe also deeper layers? So maybe you can give a short overview on what we are capable of and what is in theory capable in this regard.
At this moment, we have a current model. Basically, we have a model that is enough to prove the concept, but we are working in generate our more accuracy current models. But the possibility is that we can do this. Yes.
So, if there are no other questions or unrelated question to this specific one, I would say thanks to everyone for attending this presentation. If you think about some other questions, of course, feel free to reach out to my colleague Ricardo or also to me. And we can discuss via email, and then we can go into much more detail and even maybe give you a demonstration if you're interested. For an organizational standpoint, the next MIU will be on the 5th of July. From one of our colleagues, it will be on the project FlexiKing. If you want to stay updated about this presentation, just feel free to take a look at our website or on our LinkedIn, where we will keep you informed about upcoming MIU presentations. With this said, thanks for everyone for attending, and we will hopefully see you next time. Have a nice weekend.